Now we shall look at multivariate linear regression, and what this essentially is just telling us is you have multiple variables. That is, we have more than one variable. We have seen how we can um, develop a model for a univariate linear regression. Now let's see when we have more than one variable. Now, when we have more than one variable, which is referred to as higher dimensions, instead of just fitting a line, now what we are now fitting is a plane. That is, we're trying to fit an hyperplane. Remember that in just one variable, we are trying to try to fit just a line. But now that we now have more than one features, then what will be fitting is an hyperplane. Then it becomes more difficult to actually be able to, for humans to be able to visualize, but the computer can still be able to draw a hyperplane through the data point. For instance, if you have a two variables input, so linear regression fit a two dimension plane to the data. So this is the hyperplane, and these are our two features, x1, x2. Then you draw an hyperplane through the data point. Then you can measure the error between each of the data points and the point on the hyperplane. Okay, so we choose the one closest to the target y, and as you know, linear regression uses the mean square error, which we sum, and it's just the same intuition with fitting a straight line that we use in higher dimensions. But in this case, we are fitting the depending on the number of planes, number of variables or features, we are fitting that number of dimension to that dimension hyperplane to the data. So it's difficult to visualize for human, but the computer can easily visualize the hyperplane. So the hyperplane is defined by parameters W, which is a vector, that is d by one vector. So based on the number of dimensions that we have, so you can have a vector this way. So if you have something like this, so the number of rows will correspond to the number of dimensions. This is a vector. So now this is an example. Now scaling up our example of house prediction. Before, we have always been using just one feature, which is the square feet, but there are other features that could actually contribute to the price of the house. So it could be the number of bedrooms, the number of floors, the age of the homes, and several others. So this is now a multivariate problem. But essentially, the concept is the same. We just having one variable. The n is still the number of features, the input variables, and we just have y to be our predicted value. So now previously, because we just have only one input variable, we're referring to x. But now that we now have more than one variable, so we can refer to each of them as x1, x2, x3, x4. And if we have up to xn like that, we continue to xn. Alright. So now in this case, before we just say, okay, this is still our bias, this still remains as our bias. Before, we just said that we want to learn W1 and W0 multiplied by our x1. We remember that these are x1, which is this value, and we want to just learn what particular value of W1 will multiply with this. But now this also needs to have its own weight, which is W2. This will also have its own weight, which is W3. This will also have its own weight, which is W4. Alright, so by the time you have all those ones, all those weights, so we need to, essentially what this is trying to do is that we want to know how important is each of the features in contributing to our prediction, how important it is. So you see here that we have our x1. So if we predict that the weight for that is 0.1 and the weight for this is 0.01, the weight for this is 3, just trying to pick random values, and the weight for x4 is 2. So you could see that by the time you look at all these weight, you see that these 3 corresponds to the what, the most important or most significant, which is in this case the number of flaws. So yeah, so and now instead of just, since we now have a bunch of weight numbers, we can just represent it as a vector. So this is a vector, so we just get all our w0, w1 up to wn as a vector, and for us to be able to multiply, so this essentially transforms to this, can transform this to this point. So you could take this one, any of them, just transform this to this one. So you take all this w1, w0 up to wn, and all the x0 is it's just included here to be able to balance us. So you can just take your x0 to be equals to 1, so that it doesn't really affect the values. Yeah. Alright, like so, you can see for convenience of notation, we just take x0 to be equals to 1, so that the number of items in our vectors will be equal, so it will be easy for us to do the multiplication. So essentially we have our weight, which is a vector, we have our features, which is a vector, and to be able to multiply two vectors together, we do a transpose. So this and this are essentially the same. So this is a way of transforming this into a vector, into a weight matrices format. All right, so this is our training data, the first instance up to the nth instance, and for us to be able to get our target prediction, what you essentially do is we take the first one and we add up, which is just the same thing that we mentioned before. So our x is x0 to xn, our w is w0 to wn. We have to do a transpose of that, excuse me, so that we'll be able to do the multiplication correctly. So the parameters defines the mapping from the input to the target. So we're learning the weights vectors that will be able to tell us what values of those weight matrices will correspond an input to a target. So how do we choose our W? Essentially, it's the same thing that we have mentioned before. We do our gradient descent. Still, the gradient descent we still need to use to be able to select our W's. The gradient descent, like we mentioned, is the algorithm that helps us to be able to choose the value of the W's. So, and how does the gradient descent works? It works by iterative function and trying to do a partial derivative, like we mentioned before. So we update W by moving along the direction of the negative gradient. So we do a partial derivative of the total error based on each of the weights in our model. So this is the calculating the error based on the predicted and the actual. We have seen this before. It's just the same thing. We're calculating the mean square error. So instead of just minimizing only W1 or W0 and W1 this time around, we have to minimize all the weights together, which we refer to as the parameters. And how do we do it? This is the rule. We initialize the weight vectors. All the vectors, we give them a random value. Then we continuously do what? A partial derivative of each of the parameters. Then once we are done, then we update the parameters and then we make the change. So this is what we do. We take the value for each of the parameters. This is just the same thing we have been doing before, and we simultaneously update all the weights for from j equals to 0 up to len. Alpha is our learning rate, like we said, is used to determine how big the steps we take to down the global minimum. So when some criteria is met, maximum of the rate of decrease of error falls below some threshold. So when do we stop? We can actually stop. We can define our own criteria and says that, okay, since we are repeating this iteratively, we can say if you do it iteratively and there are no significant changes in maybe in like 5 epochs, maybe the changes are less than 0.2 or 0.1, then we can say stop. That means we have actually reached a point to which we can where the algorithm, that gradient descent, has actually converged. So we don't expect to do better anymore. We don't expect the algorithm to be able to do better. So we can actually stop when the number of criteria is met. This is essentially better from experience than just picking number of iterations. And sometimes you might actually just pick maximum iterations and your threshold might still be, your loss might still be decreasing. Alright, so gradient descent for linear regression: when you have univariate at n equals to 1 and when you have n greater than 1. So this is what you have when n equals to 1. You just have the bias and the W1. But when n is greater than 1, you have the bias and you have W1 up to Wn. And how do we choose our learning rate? These from practical experience are good choices for learning rate. You can have 0.01, 0.03. These are good choices to start with, and observe the way the loss decreases. Then you can either decide to increase or to decrease the learning rate as you observe the loss. Multivariate linear regression, if you want to model this in using a neural network, it's just, before, this is the only thing that we have. Now we need to add more, so we are now adding this now to our neural network, because now we are now having more features that we are adding. Remember, we just keep our bias to be equals to 1, just a constant, and each of the neuron goes to the output, which is each of them is having a particular directed edge to the output layer, and they have associated with each of the edge a weight matrix, which is the numbers that we're trying to actually learn, to be able to know how heavy, how significant each of these neuron is to contributing to the final value here. Okay, so that is about all for this part. We shall continue next time. Thank you for listening, and do let us know what your comment are.